Okay, yeah, good morning. Thanks for coming bright and early. So I'd like to tell you about maximal Mumford curves, also abbreviated MM curves. And this is joint work with Mario Kommer, who is a professor in Dresden, and Raluca Vlad, who is a PhD student at Brown University, jointly supervised by me and Melody Chen. So going to start with 4 fields. Okay, so the first field, C, like Dan was saying, that's a placeholder for a characteristic 0 field, sometimes algebraically closed. And so we're going to be interested in curves. These are going to be curves in projective space of some dimension, ambient space n. And we're going to be interested in smooth curves. So C is a smooth curve of genus G. People are still coming in. So I asked Mayo yesterday, what's your favorite curve? And she wasn't completely sure. So maybe by the end of the talk, you'll like one of the curves that I'll show you. Now, another field that I like and that Mario likes a lot is the field R. So R is my notation for an ordered field, sometimes real close, that is to say of index 2 in its algebraic closure. So think about the real numbers. And so we're going to assume here, of course, that the curve then is defined over the real numbers. So it's given by equations with real coefficients. And so we can also look at the real part of the curve. So the real locus has at most G plus 1 ovals. So an oval is a connected component, and over the real number, each connected component is topologically a circle. Right? So the real part, that is to say the fixed point locus of involution on the Riemann surface, is a finite union of ovals, topological circles, and the 19th century theorem from Harnack says the number of ovals is at most G plus 1. So most, if G is the, so for example, if you have a genus 3 curve, then maybe you have at most 4 ovals. Okay, so that's the situation over the real numbers. Now, for the third field, let me use the notation QP. So think p-adix, a placeholder for your favorite field with an interesting valuation. And so there in this group, people are very interested in the Berkovich skeleton, which is the ultimate tropicalization of the curve. Now, that's a graph. It's a metric graph. Let me write trop C is a complicated metric graph, but the essence is not so bad. It's a finite graph with at most G cycles. And we're going to be interested in both of these situations, both for the real case and for the valued case. We're going to be interested in the extreme situation. So here, over the real number, so if equality holds, then we say C is a maximal curve. So a maximal curve is a smooth curve, smooth projective curve defined over the real numbers that has G plus 1 ovals. Now here in the non-Archimedean situation with the Berkovich graph, if the maximum is attained, so if the equality holds, then we say C is a Mumford curve. So curve is a Mumford curve if you can see the genus as the number of oval and as the number of loops in the corresponding Berkovich skeleton. The number theorists sometimes call this bad reduction, but of course this is a value statement, right? In tropical geometry, that's the best case scenario. and we like it very much. So those are 3 situations. Please interrupt me. So I'm planning to go very, very slow in this talk. So we have now 2 notions of M. The first notion is maximal curve over the real numbers. Good morning, Marvin. We're talking about projective curves over the real numbers. They are smooth, and if they attain the Harnack bound of G+1 ovals, we call this a maximal curve. And then at the same time, we might be looking at non-Archimedean curves, and we're going to say such a curve is a Mumford curve if in the tropical graph, the Berkovich skeleton, the number on the loops, the bound on the loops is attained. Okay. The fourth and last field, let me write R curly curly epsilon. Well, that's a field that combines the best of the last 2 examples. So this is the field of a real Puiseux series. So Puiseux series with complex coefficients or an algebraically closed field. That's been sort of the blueprint of fields in the early literature in tropical geometry. And this is a real closed field of index 2. So this is an ordered field, so real numbers with a perturbation parameter epsilon. And again, we have a curve C. And now I'm going to say my curve is a maximal Mumford curve or MM curve if both equalities hold at the same time. Okay, so I would like to study curves that in their life as a real curve have the maximal number of ovals, and in their life as a non-Archimedean curve have the maximum number of loops in the Berkovich skeleton. So those are curves I'm interested in. We're going to call them MM curves. And the question I'd like to discuss is how to construct an MM curve. Anna, do you have a question?
What's the maximal over a field that's not R?
Well, it's over an ordered field, right? So over R, of course, we have a topology, right? We can talk about loops. And then over other real closed fields by standard comparison theorems or model theoretic arguments, they behave like the real numbers. So the topology is a little subtle, right? So there is a paper with this title on the archive from earlier this year. And since you all have a device in front of you, you can also look at that paper and follow along. And so some of the technicalities here, matching the 2 conflicting topologies is quite subtle, right? So, but think here over R, just think like in high school, right? You have a curve in the plane and it has circles, and these are ovals. Okay, so how to construct MM curves? Well, the first answer and the first example is to use Viro's method. So tropical geometry has a very diverse history. It has many, many fathers and mothers, and Oleg Viro is one of them. So he introduced the patchworking method for constructing real curves with prescribed topology. So he was very interested in Hilbert's 16th problem. So the Hilbert 16th problem asks for a curve real curves of a given degree in the real projective plane, what configurations of ovals are possible. Hilbert was particularly interested in degree 6 curves. They are, of course, models for K3 surfaces, right? You make a K3 surface by double covering the projective plane ramified at a sextic curve. And then there's sort of a 100-year history. So in the meantime, I would say an answer to Hilbert's problem is known up to degree 6, 7, and then partial results beyond. So this was at the very beginning of tropical geometry. So this is sort of the beginning of real tropical geometry. And to make this talk even more understandable, I have a handout. So everybody should either have one of these in front of you in the next 30 minutes, or sit next to somebody who has them in front of you, okay? So this is my handout. So I'll come back to Vero's method in a moment when everybody has the handout. Example 2 is not a Vero curve. I'm going to give you a very explicit curve in the plane of genus 3. I'm going to give you the quartic curve. So my curve is x, y, z times x plus y plus z. So this is 4 lines in the plane, topologically 4 Riemann spheres touching pairwise. So imagine 4 soccer balls that pairwise intersect. But then we perturb this a little bit by an epsilon times fyz, f of xyz. So f is a homogeneous polynomial of degree 4 with real coefficients. So I'm going to be interested in such curves. And I claim that this is a smooth maximal Mumford curve if and only if f satisfies a certain condition. If and only if f, so again, f is a polynomial with real coefficients, homogeneous of degree 4. If this is positive at the 6 intersection points of these 4 lines. So the 6 intersection points are 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, minus 1, 0, 1, 0, minus 1, and 0, 1, minus 1. Right? So if this is the case, then as a real curve, this has 4 ovals, so it's a maximal curve, and it also is a Mumford curve, meaning it has really, really wicked reduction. Okay, so everybody sees the picture and the text in front of you. Okay, so let's look at this, right? So, so at the beginning here in the text, there's a story, right? So there's the definition, or something for you to take home. Then on the lower left, you see a triangulation, a regular unimodular triangulation of 4 times the unit triangle, right? So this is a model for a tropical quartic curve in the plane. And then the next 2 pictures show how you transition between the concrete tropical curve in the plane and the Berkovich skeleton, right? So you go from the unimodular triangulation, you draw the dual graph. I like the min convention. So there's the tropical quartic. Each bounded edge has a length. And then you repackage this in the Berkovich skeleton, right? So the picture that you see on the right is the same genus 3 curve as a point in the tropicalization of M3, the moduli space of genus 3 curves, right? So this shows you, the unity of tropical geometry on the left. And on the right, there's Vero's method. So this is stolen from the book on triangulations by De Loera, Rambau, and Santos. So to quote Ben, this would be an enriched tropical curve, right? So you take the triangulation, you produce 4 copies, 1 for each of the orthons, right? You take a triangulation, you replicate it 4 times for the 4 orthons, plus, 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 minus, minus, plus, and minus, minus. Then you decorate the vertices by the signs of the coefficients, also called K star, mod K star squared in Darmstadt. And then you draw the corresponding real curve, and it all patches together to a classical curve in the limit. So this is Vero's method, okay? Very well known since 40 years and stood at the beginning of tropical geometry. Now, there are 2 big drawbacks of Vero's method, at least 2. So one is that it really works for plane curves and a little bit for complete intersection, but mostly for plane curves. And the thing is, most curves are not smooth plane curves, right? So plane quartics is okay. That's canonical curves of genus 3. But in higher genus, if you want to get all curves, you probably don't want to, certainly in the projective geometry of all curves, you don't want to work with plane models. The second reason why Viro's method is really bad in practice, so I'm an applied mathematician. I'm interested in numerical methods in algebraic geometry. And from a numerical point of view, the epsilon is just too small, right? So if you try to build curves with over the non-Archimedean field in the plane, using Viro's method, you get really horrible coefficients. So the stability of the numerical computations is very, very bad. Okay? So those are two serious drawbacks. So we're trying to think about other constructions of curves. And in the talk today, I like to talk about curves in their canonical embedding. Okay? So I'm going to be interested in canonical MM curves. So here's our first example. Now, those are coefficients are pretty nice, right? It's very easy to make a friendly polynomial that satisfies this mild positivity condition. And then I claim this is automatically a smooth MM curve. So this is the kind of construction. So I like to emphasize this construction and de-emphasize that construction in this talk. Okay. Any questions about the pictures on page 1? Is this clear? This was just a sort of reminder. So Veronica, you came here to study tropical geometry. So tropical geometry is the art of drawing and interpreting pictures like the 4 that you see at the bottom. Okay, so there's our MM curves. Now the answer I like to give to this question is the following. I like to start from a so-called graph curve. Okay, so these are curves associated with graphs. There's a paper called Graph Curves by Dave Beyer and David Eisenbud from 1991 that lays out the basic theory. Alhaides mentioned them briefly yesterday. And so those I would like to take as the point of departure. So a graph curve is defined. To describe a graph curve, you start with a simple, undirected. I'm going to start with a simple, undirected, trivalent connected graph. So for example, if the graph I start with is the complete graph on 4 nodes, so K is K4, then the corresponding curve consists of 4 lines in the plane. Right? So this is a reducible quartic curve consisting of 4 lines in the plane, and then the corresponding graph, a dual graph, has 1 node for every irreducible component, and then 2 nodes are connected by an edge if they intersected in the graph. So just to kind of illustrate this, so each intersection point here corresponds to an edge in the graph. So for now, this is just a graph, no weights or length to the edges. But of course, many of you already think about this as an arithmetic surface with a nice rational number attached here that then serves as the length here. Okay, these are graph curves. Another one graph that we maybe like is this graph. Let's look at the edge graph of a 3-dimensional cube, right? So maybe this graph. Now this graph, what's the genus of this graph? So it's early in the morning. So take the edge graph of a 3-dimensional cube. And people in the first row never get asked questions, but people in the last row, what's the genus of the edge graph of the 3-dimensional cube? 5. Okay. So the genus is the number of edges minus the number of vertices plus 1. Right? So this has 12 edges minus 8 vertices plus 1. And the experts quickly recognize this as a genus 5 graph. Right? So the corresponding. In
planar picture, you count the all.
You can also count the holes. We will count the holes, exactly. So, okay, so you see planar graphs in the titles. Let's count the holes. 1, 2, 3, 4, 5. No, 1, 2, 3, 4, 5. And that's the 5. Okay. Very good. Okay. Now there's a corresponding curve, a corresponding canonical curve lives in 4-dimensional space, and it will be a curve consisting of 8 straight lines in P4, and then any line intersects 3 other lines, and the combinatorial intersection pattern is the one that's given here. So let's do a numerical example. This would be example 3. N equals 4, G equals 5. So this will be my MM curve based on the 3-dimensional cube with coefficients that are much more happy and more friendly than those you get from Vero. So I'm going to take the following equation, xy minus epsilon f, zv minus epsilon g, and my third equation is w x plus y plus z plus v plus w minus epsilon h, and all this is 0. So in my projective space here, I take homogeneous coordinates x, y, z, v, and w for my 5 homogeneous coordinates. And I'm going to look at this equation. And then f, g, and h are quadratic forms in those 5 variables with friendly real coefficients. And friendly real coefficients means the following, where f, g, h are quadratic forms. They have 12 terms each. Now, of course, in general, a quadratic form in 5 variables will have 15 terms, right? A symmetric 5 by 5 matrix has 15 entries, but I always remove, I can, without loss of generality, drop the coefficients of x, y, z, v, and wx, because I can substitute by this relation, right? So I'm going to assume that f, g, and h are linear combinations, real linear combinations of the 12 quadratic monomials other than the blue underlined monomials. Okay, and there are 12 inequalities in the 36 parameters. Well, the 36 parameters are the 12 coefficients of f, the 12 coefficients of g, and the 12 coefficients of h. And I like to stipulate inequalities that are like this positivity condition here. So I like to write a positivity condition like this one, which ensures that this is an MM curve, which ensure that C is an MM curve. Okay, now I'll tell you what they are in a moment. I'll tell you what these conditions are. Now, in a situation like this, the Mumford property is easy because by design, when epsilon is 0, this is our graph curve. Right? So if you set epsilon to 0, you have a product of 2 linear forms, another product of 2 linear forms, and another product of 2 linear forms. And if you take 3 products of linear forms in P4, then that will define precisely this graph curve. So it's another easy canonical curve of genus 4, which is the intersection of 3 quadrics. So the Mumford condition is easy. The non-trivial condition here is this is supposed to have 6 ovals. Okay, so the exercise for students of Thorsten Theobald, is for small value of epsilon, maybe epsilon is 0.01, verify that this curve over the real numbers has 6 connected components. Okay, well, that's the slightly non-trivial part. Let me give you one solution to make my point that this construction is more friendly than 0. So you could take f to be z squared plus b squared, and g to be x squared plus y squared, and take h to be x plus y times z plus v. So this choice will work. So I claim there is some system of inequalities, and I claim that these coefficients will satisfy this. So this is a concrete instance of a canonical MM curve of genus 5. Yes, Dan.
Maybe this is out of place. So tropical, you are looking for a tropical way to access maximal curves. Why just maximal curves? I mean, wouldn't you want to have a tropical realization of any?
Well, I am interested in all MM curves. So I'm interested in the space of MM curves of genus G. So this is a subdomain of MG, right? But this is an interesting subdomain because we're looking at 2 semi-algebraic structures on the moduli space. On the one hand, we have the real structures over the real numbers. So it's semi-algebraic in the usual real sense, okay? On the other hand, it's a semi-algebraic domain in the non-Archimedean sense, right? So we're interested in subsets of moduli space that are twice semi-algebraic. Semi-algebraic in the sense of ordered fields, and semi-algebraic in the sense of Lauser and friends in the non-Archimedean. Is this clear? So I want to describe the correct locus in M5, and I've given you 1 point.
One of the interesting locus. Have an interesting locus for any number of over.
No, that's true. You could look also at other numbers. Okay, so I would argue that for various reasons, the maximum number of ovals are particularly interesting. Okay, so this is my case for the aficionados of Tevelev degree, for example. If you look in the original paper of Tevelev on this, it's really maximal curves that drive the 2 to the G. Right? So I would say in many applications, you're absolutely right. I could certainly look at, in this situation, so this will be a curve where the Berkovich skeleton has 5 loops and the real curve has 6 loops. I could also look at 3 loops and 2 loops and 4 loops. Those would also be interesting. But in this talk and in this paper, we're looking at the maximal case. So genus 5, that means Berkovich skeleton with 5 cycles and the real curve with 6 ovals. Absolutely. But all of these, I claim, are interesting. This is a subdivision of moduli space into interesting pieces. And what makes them interesting is that you have 2 types of inequalities. You have the usual semi-algebraic condition inequalities of real numbers being positive, and valuative inequalities saying that the valuation of a polynomial is bigger than the valuation of some other polynomial. Okay, any other questions? Okay, let me give you a lemma and then the theorem. This talk is one theorem. It has one lemma and one theorem. So the lemma is lemma 4.1 in the paper. So if you have a graph G, again, simple trivalent, let's say, of genus G, then the corresponding graph curve is, of course, very reducible, but it represents a smooth point on the Hilbert scheme. Okay, so let me write HG for the Hilbert scheme. So this is the Hilbert scheme of all subschemes of a projective space of dimension g minus 1 with the correct Hilbert polynomial for a canonical curve. Now, this Hilbert scheme has tons of components. It's a very, very complicated object. And so I will simply mean the distinguished component. So Hg, yes, question?
Don't we have many different choices for curves associated to a graph? Are we just choosing any one?
No, for the graph, there's up to projective transform. Okay, I should have said that. So if you draw the graph up to projective transformation, there is a unique realization. Right? So if you draw a graph like this, then of course there are many different ways. You could pick eight lines in four-dimensional space, but they're all equivalent up to projective transformation. So under this hypothesis of trivalent, there will be unique curve. Yes, so CG is a unique curve. So this unique curve gives us a point in the Hilbert scheme, and on this Hilbert scheme, it will be a smooth point, will be a non-singular point. Now, this Hilbert scheme, let's talk for a second. So I mean the main component. So I don't mean all the Murphy's law stuff out there. I mean the main component that governs the canonical curves. So the dimension of this Hilbert scheme of this component is g squared plus 3g minus 4. So what I'm saying, the tangent space of this point at the Hilbert scheme, which you compute in Macaulay 2 with the one-line command hom I, s mod I, right? So that tangent space has this dimension. Okay, so this is the statement. Now let's contemplate this number for a moment. So this number is g squared minus 1 plus 3g minus 3. So this number is the dimension of the projective linear group, invertible G by G matrices up to scale, plus the dimension of the moduli space. So write this down. So this, the two ingredients, there's the dimension of the moduli space, which is 3g minus 3. And then we still have the group of projective transformations on the ambient G minus 1 dimensional projective space. And this point is a smooth point in the Hilbert scheme. So at least locally, we can make happy deformations. Let's do just one more example to kind of get a bit used to this. Right, let me draw another graph that I like. So here is a genus 4 graph. So this is a planar graph, and for a planar graph, as Dan said, we can count regions, 1, 2, 3, 4. So that's a genus 4 graph, and this gives us a curve in 3 space. I'm going to make curves in 3 space, right? So this picture represents a unique, up to projective transformation, William, a unique configuration of 6 points, 6 lines in 3 space, with this intersection pattern. Let me give you another one. So another graph of the same genus would be K33. So both of these, did I do this correct? So both of these have 6 vertices and 9 edges. So the curve consists of 6 lines and has 9 nodal singularities. But this one is planar, and this one is not planar. Right? So not planar, but these represent unique curves. And so here is the Toblerone graph that is planar, and that's the complete bipartite graph 3,3 that is not planar. And this number here is 24. Right? So there's 9 dimensions for the moduli space, and there's 15 dimensions for projective transformations. 9 dimensions, 1 dimension for every edge of the graph.
Why is this easy? Smooth point, there's many different linear points.
Well, I claim every point exactly is a smooth point on the Hilbert scheme. it's also semi-stable. It's also a nice point on moduli space. So I'm saying this is a nice point, right? So this is a nice point on the Hilbert scheme, but if you mod out by projective transformations, then you get a nice point. Then you get it unique. Okay. Very good. So a math lecture should have necessary ingredient in a math lecture is at least one theorem and one joke, and they shouldn't be the same. So now comes the theorem. Let me state the theorem. Okay, maybe I'll do this here. While I'm erasing, you can start enjoying the colorful picture on the back side of the handout. Okay, so this is the theorem. 1.4. And the theorem has 4 parts. Okay, so the first part is, it says an MM curve, a canonical MM curve with special fiber CG. So and this is our graph curve in PG minus 1. Of course, you're correct, right? In PG minus 1, there's an orbit under my group, but I'll use the definite article, speak about the curve. So an MM curve with this special fiber exists if and only if G is a planar graph. Yeah, so it's the maximal condition that fails. So here in this vicinity of this graph curve, there are there's a whole neighborhood of curves with 5 ovals. So it's a canonical curve of genus 4 with 5 ovals. And they are Mumford by construction, but the point is they will be maximal 5 ovals. Here you find many happy Mumford curves, but none of them will be maximal. None of them will have 5 ovals. That's the first statement. Second statement, the locus of such curves is full dimensional in the Hilbert scheme. Okay. So the tangent space statement is a infinitesimal statement. What I'm saying is we cannot just infinitesimally deform, but we can actually deform. We can actually build these curves. So the gentleman from Lancaster, I forgot, that's Ben, right? Maybe. So there's rigidity theory. The world capital of rigidity theory is Lancaster. So this is the difference between local and global rigidity. Right? So we can actually carry out a deformation. So the locus is full dimensional in the Hilbert scheme and therefore in the moduli space. So there's a full dimensional set. But this set requires a little contemplation, right? Because we both have the real topology and the non-Archimedean. More precisely, every first order deformation that is to say, every vector in the tangent space, and again, for the students, the reason functors of points are so nice, right? The reasons why we think of a scheme as a functor that eats a ring and makes a set, because you can go to Macaulay 2 and quickly compute tangent spaces. Right? All you need to say is hom I, comma, s mod I, close parenthesis. So in this vector space that I just recited for you, every first order deformation that satisfies a system of linear inequalities from a cone. This is a convex polyhedral cone, and it's a cone isomorphic to R g squared minus 1 times R g3 minus 3 in the, I'll finish the sentence, in the tangent space of HG at the graph curve lifts to a maximal Mumford curve. Okay, so I have this point, and I'm going to use the definite article. So I have this point. Now, at this point, I have this very nice tangent space of the correct dimension. It's a smooth point. In this tangent space, this is a real vector space. Okay, in a real vector space, you have polyhedra and linear programming and all that. So in this real vector space, I'm imposing one linear inequality for each edge of the graph curve. So the graph curve has 3g minus 3 edges, and I'm going to impose one linear inequality on this finite dimensional vector space that defines a cone. This cone has a linearity space of dimension g squared minus g, so it looks like this. It has a linearity space, and the linearity space accounts for the non-uniqueness. So the linearity space is the Lie algebra of PGL. Right? Okay, so I have the linearity space of my cone is the Lie algebra, but then the actual inequalities come from the edges. And then as long as you're in this cone, as long as it looks like you can make a deformation, you can actually make a deformation. And as another converse, every such lift is an MM curve. So what this I mean, if the tangent vector, if you have a deformation, any deformation, and if it's a real deformation, the tangent vector satisfies those inequalities, then you actually get an MM curve. Yes, question.
Then take the other signs, you get the other numbers of all those signs.
If you take the other signs, you get other things. That is correct. Okay, so it's clear. Does anybody other than Dan have a question? Yes.
So you, as far as I understand, you take every planar graph, you take the points of the Hilbert scheme, and then you sort of get little neighborhoods around these. Right? Do these little neighborhoods cover the locus of maximal Mumford?
No, there are maximal Mumford curves further out, right? Vero, for example, and other constructions. So there'll be other things out there. This is simply just in a neighborhood of the graph curves.
Right.
Good question. Yes. Okay. Yes.
So this cone, is this like maximal in the tangent space?
It's a full dimensional cone, right? So the dimension of the tangent space, so this is the dimension of the tangent space, which is also the dimension of the Hilbert scheme. And it's a full dimensional cone because this number plus this number is the number over there. Okay, well, now let's look at the picture. Let's carry this out, okay? So this is an example where the curve is a bit more interesting, where it's sort of not a complete intersection. So there's a genus 5 graph on the left. This is figure 1 in the paper. So in the upper left, you see a genus 5 graph. And in the lower left, you see a depiction of the graph curve, right? So, of course, this is a curve in P4, right? So there's a curve in 4-dimensional projective space given by 9 lines. And on the left, you see a planar drawing, but you can see there's crossing over and crossing under. So I indicated intersection points by white circles. So the lines are called 1, 2, 3, 4, 5, 6, 7, 8. In the lower left, you see sort of a planar projection, a cartoon of the graph curve in P4. And each line meets 3 other lines. For example, the line 2 meets the lines 1, 3, and 5. Is this clear? Right, so that's the graph on the upper left. and the graph curve on the lower left. Now on the upper right, you see a collection in the graph of 6 cycles. So I'm organizing the 6 regions, including the exterior region, and I'm going to draw one cycle close to the curve, to this graph in these regions. There are 5 bounded regions. There's 1 exterior region. And in this drawing, every edge of the graph corresponds to 2 colorful pieces of these ovals. Some people call this a ribbon graph. Okay. And the lower right, you see the actual curve with 6 ovals. Right? So you do the algebra, right? So anyway, locally, when 2 lines meet like this takes place inside some plane. And this plane, by playing with the coefficients of the local equations, there are 2 ways you could deform the curve. You can either deform it this way, or you can deform it that way, right? There are 2 possibilities. Like, for example, in the plane, if you have the equation x, y equals 0, and you smooth this out over the real numbers, right? There are these 2 possibilities, and this is the degrees of freedom, and you have to do exactly the right thing that's told you from the planar graph. And as Dan also said, for other sign configurations, other things will happen, right? So you have to do the puzzle, and in this case, you do the lower right puzzle the way it's prescribed to you on the upper right, and you get a cartoon of the curve, and in fact, all curves described in this thing. Okay. This clear? Okay, then let me slowly come.
There's a question from
Yes.
the
Okay.
virtual audience. Are all graphs trivalent?
No, not in general. I will assume in the paper, for the most part, we assume trivalent. So some of our results work for all graphs, but we focused on the top layer in tropical MG, where you have all trivalent graphs. Okay. Well, let me end. Hi, Ilya. So let me end by telling you what the sections of the paper are. So there's an invitation to actually read the paper, right? So 2 gives a reprise of real algebraic geometry with valuations. And this is a little bit tricky, right? Because you have to combine this sort of high spool intuition of what's true over the real numbers with the tropical intuition reflecting non-Archimedean geometry. And you need statements like, so I'm saying something is true with epsilon being a field element. That's the case if and only if there exists an epsilon 0, such that for all real numbers, epsilon between 0 and epsilon 0, something is true. So you find statements of this type. And so even if you don't care about curves and you don't have a favorite curve, but maybe you have a younger sister who believes in real numbers, this might be a good section to read. Then the sort of setup of graph curves and planar graphs. That's section 3. Then the hyperplane arrangement is constructed. Section 4 is called hyperplane arrangements at the Hilbert scheme. So this describes our arrangement of hyperplanes. Then the construction is finally carried out, constructing curves. And of course, I already confessed that I'm an applied mathematician, so we like computations. So there's an implementation, there's a math repo page where you can look at the implementation. and it works. Right? So you can draw a graph and you get equations like the one that you've seen. Okay? Let me maybe say a word about the main algorithm. That's algorithm 6.1. I'll just tell you what's the input and what's the output, and I'll spare you the steps. So the input, and now it's a three-connected, trivalent, so for the person on the Zoom. So here we're assuming, for the algorithm, we're assuming the graph is trivalent, a planar graph, because the theorem says we should be planar graph of genus G. And the output is an adapted basis of the tangent space. So this is the tangent space at the graph curve of the main component of the Hilbert scheme. And by adapted basis, I mean a basis, an explicit basis for the vector space where the first G squared minus 1 basis vectors span the Lie algebra, that is to span the linearity space. And then the last 3G minus 3 basis vectors span the moduli information, and they give us the linear inequalities that describe the cone. Okay, so you're invited to try this out, to look at the paper. I'm going to end with a word about the motivation. So one motivation for me is connections to particle physics. So I recently got into a project called Positive Geometry for Particle Physics and Cosmology. Now, we don't quite know yet exactly what positive geometry is. There's a technical definition in the literature, but part of the project is to sort of map out the scope. But whatever tropical geometry is, it will involve the trinity of complex, whatever positive geometry is, it will involve the trinity of complex, real, and tropical algebraic geometry. With that, I thank for your attention.